So, what is your magnetic stuff here? Inductor. Huh? So, usually I mean you simply, so far we had been considering only this RDCR, this is here, but in reality this is not true actually. This is for like a DC model, but if you look at a AC model, then this will have one more resistance, and it will have parasitic capacitor also, Cp. This is the actual model of the inductor when you start considering magnetic losses. So, this represents magnetic losses which are your core loss and skin effect loss due to AC current, and RDCR is, which loss is that? Resistive loss, huh? Due to RMS current. Which is mainly due to winding. Okay. So, these inductors have a coil, the windings, and that will have some finite resistance. So, that is what it represents. So, measuring RDCR is very easy. Okay. You can simply use the ohm meter. Okay. So, use your multimeter, set on the ohm and just click, basically apply your probes on across two terminals and you will see RDCR, or you insert some DC current and look at the voltage, how much it is dropping across that. So, IR drop will also give you the, tell you the resistance, but RACR is not simple. You have to have a AC current flowing into that, and we know that inductor current is always AC, there is no like a DC current, it has some ripple amount on top of that which contributes to the AC losses. So, your DC loss or RMS loss, I would say, you represent IRMS, ILRMS I would say, which means inductor RMS current multiplied by RDCR, and AC loss you represent IL AC square into RACR. Okay, so, in the RMS you have both ripple component and DC component, but in AC loss you only have a ripple component. So, this is nothing but inductor ripple current, no DC current. So, if a ripple is larger, then this loss will increase. Okay. And what if I want to write the Q of this inductor, what will be the Q? Omega L over R, total R, and total R is plus RACR. And you know, if Q is less, then losses will be high, inductor will be poor. Okay. So, I mean Q defines by how lossy your inductor is. Okay. So, we usually we want very high Q, means we have to minimize RDCR and RECR. So, let us say you are using inductor which has a very negligible RDCR, but if your RACR is very high, then choosing the inductor with a very low DCR may not help much in that case, because you know there are ripples in the current and which may contribute to these core losses more, and it will kill your efficiency. Okay. And since it is a AC component, so it will also depend on your switching frequency. Okay. So, usually this is not given in the data sheet, you have to measure. So, you have to characterize the inductor with the AC current and then measure the AC losses, and sometimes on request they give, but usually in the data sheet they will not specify this number. Okay. And these are dominant at high frequency. So, some of the data sheet may give you the Q actually. Okay. So, it may look like a something band pass filter Q. Okay. So, wherever you have the Q of the inductor peaking, you choose the switching frequency according to that. Okay. Or if you have already selected your FSW, then you pick the inductor which gives you the highest Q around that frequency, so that you can get a better efficiency. So, choose FSW closer to F naught. So, later I will show you guys some data sheets, what are different parameters are given in the data sheet and how you read that basically, and when you, so when we actually start designing how you design, what are how you start designing your, so how you choose your L and C and everything. So, we will look at the data sheets of inductor, capacitor, everything, and what are different components or parameters are given in the data sheet, which you take into account when you select an inductor or capacitor. So, now we know what are different losses. So, what will be the P loss, total P loss? Conduction loss plus P gate plus PSW plus P, what do I call it? So, let us give it some name. Okay. PSC. So, this is your I square R component, which is nothing but conduction loss. This is your CV square F, gate driver loss. This is your half of, sorry, not half. How much was that? Twice of VF into I load. So, I am just writing I. This is your dead time. This was your half of T on plus T off V dd into I. Okay. Hard switching loss. Let's move it, create some space. P of AC. And this is your ISC square into RSC. Okay. There is one more loss. RMS is already, this is RMS actually. Okay. Where? Yeah, so that's why I am writing IRMS. Huh? There is something called P of Q. Quiescent current, quiescent loss. This is your VDD into IQ. And what is IQ? This is IQ is current associated with controller. So, you have a controller in the feedback. Huh? So, that is not like lossless. There will be some current that will require. So, you have a band gap there, you have a comparators, you have error amplifier. So, all those currents, and this is what starts dominating at very low current when all other. So, your magnetic losses usually if you operate in PFM. So, since it is a factor of AC, okay, so you are operating at a lower switching frequency. So, your magnetic losses will not be that dominant, and at light load we already talked about. There is a one way you improve the efficiency by reducing the frequency. So, at light load you usually switch at very light load, but this IQ will be fixed. It is not going to change because controller is on. So, your gate driver loss will also go very low, your dead time loss will also go very low, conduction loss already will be low because you are not operating at very high load. So, the IQ will start dominating. So, your efficiency will be mostly determined by IQ current. So, that is why at light load your PQ is very important. So, you try to design your controller with very low current. Okay. So, now time to look at this graph. So, this is a normalized loss. Normalized means consider your loss is 100%, total loss is 100%. Okay. So, it is showing which one is dominant at what point. So, when your load is very high, so what is this? This guy is, yeah. So, this is your switching loss and this is your other losses and channel conduction loss. This is not switching loss, this is channel conduction loss. Yeah, this channel conduction loss, because this flat is a plus actually. They have drawn a longer line, that is why. So, it is a plus and this is cross. So, this is switching, this guy, correct. Let me write it here to. So, this is your and this is your Okay. So, what will happen at very high load? Your conduction loss will start dominating, okay, and that is what you see here. As current is increasing, this conduction loss is getting higher, and rest of the losses will, they are associated with switching. Okay. So, this will I square R loss will dominate. So, and that is why you have this. And if you look at the switching this loss, these are other losses that will have magnetic loss and all those actually, which they have not shown is separately. Okay. So, if you further go higher current, load current, you will see this will start reducing, but this will keep increasing, because I is increasing, R is fixed. So, I square R loss will keep increasing at light load, at high load. No, but that is a, how you have to look which factor is dominating. That has a square factor. Conduction loss has a square factor. So, if you make the current double, that will change by 4, increase by 4x. So, percentage wise this will be more and other will be less. Okay. It is a relative. It is, you should not look at absolute number. Absolute both will increase, but which one is dominant compared to other, that is what you have to look. Okay. Then at somewhere in the mid load, so let us say 100 milliamp or so, your conduction loss may not be that dominant, because I square factor will be less, but your switching loss may start dominating there. Okay. So, you see here switching loss is peaking closer to 100 milliamp here, and this is for one particular design. Different designs may have this peak at different current. So, that is not necessary as such. Then if you look at this gate drive, so what is a gate drive? Is a fixed loss. Okay. So, if your I square loss is very high, this will be a small fraction, but if your I square loss is very low, then this may be very small. So, the total loss here may be very high here, and the total loss here might be low, but what we are looking at here is the relative number, and efficiency is also relative number, how much you are delivering compared to how much you are losing. Okay. So, do not think that if you are losing a 100 milliwatt here, so you will be losing the 100 milliwatt here also, that is not necessary. But you might be delivering maybe a 2 watt or 3 watt here when you are losing 100 milliwatt, and when you are losing 10 milliwatt, you might be delivering only 100 milliwatt that point. So, you are losing 10. So, percentage wise you might be, your efficiency might be less at light load compared to the high load. Okay. So, if you look at a so the quiescent current, this one. So, look at a very light load, this is a how much 0.01. Okay. So, I mean this is dominating and this is the gate drive. So, look at this gate drive and quiescent current now dominating here. Now, think about if I reduce the switching frequency. If you reduce the switching frequency, this will start dropping. So, this is with the case where they are not doing anything with the switching frequency. Then I can bring it down, and this 20% may increase relative to this. So, this will start dominating, maybe this may become a 60% and this guy may become 20% in that case, and rest 20% will be contributed by other losses. Okay. And that is what happens when you go to very light load. Let us say you go to 10 microamp or so, and your total power consumption in current consumption in your controller is let us say 50 microamp, then that 50 microamp will be dominating over 10 microamp load current. Okay. So, you should know at what point, at what load current which will be dominant, and that is how you improve your efficiency by taking a proper step in the design. At what point you have to reduce the gate cap, at what point you have to reduce the switching frequency, and at very light load there is also possibility that you can reduce the IQ by reducing the controller current also. So, you can use a dynamic biasing, let us say. So, error amplifier you know it is not switching at very high frequency. So, you do not need very fast comparator and very fast amplify at that point. So, you can reduce the bandwidth or reduce the speed of your comparator by reducing the current. So, you can achieve some extra efficiency at light load by doing that as well. Okay.